Today we're going to look at alkanes and hybridization. Hybridization should be a review of a concept that we've seen in previous classes, as well as briefly in this course. Alkanes represent new material, but you might have seen them before. Alkanes are the simplest type of hydrocarbon. They have three things make an alkane. First, the alkanes are made of carbons and hydrogens only. There's no other atoms. All of the bonds are single bonds, and all of the carbons are sp3 hybridized. Once you've met those three criteria, then you're dealing with an alkane. And we name the alkane based on the number of carbons found in the alkane. Here in this nicer looking blue table, I have a list of kind of the pattern, and then over here I kind of filled in the gap. So let's walk through this. Methane is an alkane that has one carbon, ethane has two carbons, propane has three carbons, and butane has four carbons. The prefix on these ones doesn't inherently mean anything numerical, but by the time we got to pentane, then we switched over to a numerical format. So pent, like a pentagon, tells us that there are 5 carbons. Hexane is 6 carbons, heptane is 7 carbons, octane is 8 carbons, nonane is 9, and decane is 10 carbons. You do need to know this list, 1 through 10. You should be able to see a number of carbons and identify the name based on this chart right here, and the little addendum over to the side. Let's go ahead and take a look at different alkanes using ChemDraw. ChemDraw has kind of a cool feature where it will automatically generate names for things. Most of the time these names are correct, so we're going to convert structure to name. Okay, so the nice part about this, it will auto update. What I mean by that is when I have a 2 carbon group here like ethane, it will name it ethane, and as soon as I add in a 3rd carbon right there, it will automatically update to propane. A couple of things. One is you'll notice that I didn't start at methane, I started at ethane, and the reason for that is you can't really draw a carbon skeleton diagram of methane, simply because what would you draw? Just like a point in space. So nobody bothers. But we can, let's see, oops, there we go. There's a hotkey, I just had to remember what it was. So here we have methane, CH4. We have propane. If you go back and look at what I had originally drawn here is ethane, what you'll notice is that it gives a little red line right there. And the reason for that is, generally speaking, we don't make a single line ethane. We don't show carbon skeleton diagrams for ethane because, well, that's kind of indistinguishable from the letter L or a capital I, like iodine. So it's kind of hard just to draw a single line and call it anything. So we typically don't use the carbon skeleton diagrams until we get to propane. You can get from propane, here is butane, and then we just keep tacking carbons on and we march through the family. Pentane and hexane, heptane. You don't know about alkenes yet, so you didn't see that. This is octane, nonane, and finally decane. Okay, so there's all 10 carbons, and we can kind of build them, and ChemDraw will automatically name them. If I think I cut this thing in half, it will give me 2 separate names. Here's 2 pentanes now. I just kind of broke it in half. Let's keep this off to the side. The reason, now there are very few times in life that a chemist would encounter a straight chain alkane like this. Instead, what we tend to see is that these things pick up branches. And what I mean by that is that it's not necessarily a straight chain. It's a straight chain with some type of growth coming off of it. This growth is called a substituent, and this is referred to as the parent chain. The parent chain is the longest continuous chunk of carbons. And so the first rule when you're naming an organic molecule is to count and find that longest stretch of carbons. Once you've established the longest continuous chunk of carbons, then you give it the parent chain name of pentane, and then you state the substituent. The substituent follows the same naming rules. If it's 1 carbon, it would be methane, but when it's a substituent, instead of ending in ane, it ends in yl. So that's where the methyl comes from. It's a 1 carbon substituent that's hanging off of the pentane. And finally, we have to decide what number of the pentane the substituent is coming off of. And these words matter, so I'm going to go ahead and put some labels in here that this is the parent chain right here. Let's drop an arrow on that one. This is the name for the parent chain. This right here is referred to as the substituent. And then the other word that matters is the locant. The locant is actually the number. So we have the locant. Let's get that methane out of there. And the locant is the number. The substituent is the name of the chunk of carbons that are hanging off. And then finally we have the parent chain. So why is the locant important? Well, what happens if I put the methyl group here in the center position? Well, notice that it's still a methyl group. The parent chain is still a pentane, but now it's coming off of the third carbon. And we always number from whatever end is closest to that substituent. So you would not call this compound 4-methylpentane because you want to try to number from the end that's closest out here to the substituent itself. Here it doesn't matter which side I start numbering from. I'm going to get to the third carbon and that methyl group the same either way. If instead now this is an ethyl group, then it would be 3-ethylpentane. And if we continue to grow this out into a propyl group, what you're going to see is it's going to change the parent chain name. So this is, I'm going to let go of my mouse, and now it's 3-ethylhexane. And what it did is before, when it was 3-ethylpentane right here, this was the parent chain. 1, 2, 3, 4, 5. And the ethyl group was coming off with the 3 position. But as soon as I put that other carbon in there, now my parent chain is no longer 1, 2, 3, 4, 5. The parent chain is the longest continuous stretch of carbons, which is now 1, 2, 3, 4, 5, 6. So that's why the parent chain changed from a pentane to a hexane, because I just found a longer stretch. So there's no memory, like it's not like these compounds remember what used to be the parent chain and always require that to be the parent chain. As you grow these substituents, you can fundamentally rearrange your parent chain. Let's go back to the simpler example of 3-methylpentane right here, and now let's put a second methyl group in there. Now it's still pentane. That's still my longest continuous chunk of carbons. 1, 2, 3, 4, 5. You could also call this your parent chain if you're so inclined. 1, 2, 3, 4, 5. It doesn't matter as long as it's the longest continuous stretch of carbons. But now we have 2 methyl groups. One of them is at the 2 position and one of them is at the 3 position. The 2 methyl groups are lumped together as dimethyl, and then their locants are separated by commas. So this is 2,3-dimethylpentane. I'm going to draw another compound, and let's see if you can name it. So we'll go ahead and draw in a parent chain right here, and then I'm going to put some substituents on it like this. All right, I would encourage you to pause the video and then see if you can name this compound right here. I'm going to cheat and go ahead and convert structure to name, and this is 2,4-dimethylpentane. Now you should start asking some questions about what if. For example, what if we put 2 carbons on the same position, 2 methyl groups here, and then we have 2,2,4-trimethylpentane, and then what if instead one of them is an ethyl group? Well, actually that just changed my parent chain to 1, 2, 3, 4, 5, 6. So now it's a trimethylhexane, but let's make this right here. And now we have both ethyl groups and methyl groups present in the compound. There is an infinite degree of complexity that you can get to with alkane nomenclature. For today, we want to look at identifying the parent chain and then identifying substituents that are coming off of the parent chain. The only kind of extra level of complexity that I want to show you is this. Let's go ahead and get rid of this ethane right here. And we're going to call this, we're going to go ahead and make it into a heptane. All right, so here's my parent chain, 1, 2, 3, 4, 5, 6, 7. This is a well-behaved parent chain because it just goes from left to right. It's exactly the way we read, and so it's what we're inclined to look for as a parent chain. But you can't stop with just looking left to right. You have to explore all possibilities of different chains to make sure that you truly end up with the longest continuous chunk of carbons. And that's definitely, it's not hard to do, you just have to remember to do it every time. Okay, what you'll notice is that my first branch occurs at the 2 position, and that's a methyl group, and my second branch occurs at the 4 position, and that's my ethyl group. The methyl is written after the ethyl because these substituents, which are the things hanging off the parent chain, are placed in alphabetic order. So, what have we learned today? Naming alkanes. Okay, first step, find the longest continuous chain of carbons. And that's your parent chain. And we're going to name that one. Name this parent chain. Whoa, I was doing so well typing. With an, we want to do an ane ending. And then find all substituents. Substituents. And name with ill endings. And then you number. We're going to say that, actually we're going to use the technically correct term here. We're going to assign locants. Okay. So those are kind of the 4 rules that you want to use for naming these different compounds. And that's what we've done here on these various compounds that we've got. I'll go ahead and clean this up just a tad so that I can dump it over on my PowerPoint. Let's go ahead. I think the space will hold one more figure nicely. So let's go ahead and drop one more in here. 1, 2, just to have a more complicated example of something. So we're going to go ahead and do this, and then I'm going to put a branch here and a branch here, and we'll do a branch there. And let's go ahead and make this one more branch. We'll be pretty creative here. Oh, I wanted to go the other direction. All right. Once I finish this, oh, come on. Okay. I would encourage you again to pause the video and follow these 4 rules up here and see if you can name this compound. Let's see how you did. I think one of the challenges of this compound is finding that longest continuous stretch of carbons. So we don't want to just go left to right if that's where we start. So if we go from left to right, it's 1, 2, 3, 4, 5, 6, 7. But if I start here, it's 1, 2, 3, 4, 5, 6, 7, 8. And if I start here, 1, 2, 3, 4, 5, 6, 7, 8, 9. That right there is my longest continuous stretch of carbons. And so let's see, I'm going to get fancy here. And we'll go ahead and color that in. This is probably not worth the time it's going to take me. I have a mouse. I definitely couldn't do this with a trackpad. All right, and we'll color this all red. So now my parent chain is colored in red. This is some type of nonane. Coming off of the nonane, I have 2 methyl groups and 2 ethyl groups. So I have nonane as my parent chain. And then I have a diethyl and I have a dimethyl. As far as numbering the parent chain, this over here is going to be the number 1 position, or this right here will be the number 1 position. And we're going to go until we find the very first branch. So if we go start here, we don't encounter the first branch until 2, 3, 4. So our first branch will be at the 4 position. If I start over here, then my first branch is at the 3 position. There's some additional complexity we're going to learn about later on, but for now, the first branch, if the numbers are different, then it's easy to say that this is the number 1 position, and therefore my methyl groups are coming off of the 3 and the 4 positions. Numbers are always separated from numbers by commas, and numbers and letters are separated by hyphens. And that is an important piece of punctuation. At the 5, this is the 5 and the 6 positions. I have my ethyl groups, 5, 6 dash ethyl, dash diethyl. And alphabetically, we place these things in alphabetic order But when we do that, we always ignore any type of numeric designation. So di here is a numeric designation. So I don't even look at that when I'm alphabetizing this. I'm looking at it as an E versus an M. And E comes alphabetically first. And so it's going to go 5,6 diethyl. And numbers and letters are always separated by hyphens. Numbers and numbers are separated by commas. And then dimethyl, and now the nonane just goes on the end, and there are no spaces in these. Letters are not separated from letters. So here is the correct name for this compound right here. For the last part of today's lecture, which is kind of the bigger part, I want to talk about these 3D representations. This particular way of diagramming out molecules, it is shown in your textbook, but never very well explained. So I want to really pause for a second and look at how we get to these particular diagrams. So I'm going to go back into ChemDraw, and we'll start over again. File, new document. Zoom in a bit. Let's talk about methane. So methane is carbon with 4 hydrogens. So we've got a carbon here, 4 hydrogens coming off of it. You can actually, okay, here's methane. The first thing that you want to do is determine what the hybridization of the carbon is. Hybridization is based on the number of electron groups. And so if we have 2 electron groups, then it's going to be sp hybridized, and 3 electron groups, it's sp2, and 4 electron groups is sp3. And this is how it's always going to be in organic chemistry. I'm trying to think of exceptions, but this is true enough. So based on the number of electron groups, this carbon right here is hybridized. It's sp3 hybridized. Now, what does sp3 hybridization look like? Well, that's a great question. Let's go ahead and start drawing out some of these orbitals. I want a line. All right, if you remember, the orbital notation diagram for carbon looks like this. Carbon has 6 total valence electrons, but only 4 of those, 6 total electrons. It has 4 valence electrons. So carbon, after we go ahead and talk about helium, carbon is a 2s2, 2p2. If you remember, this is called electron configuration, and this is just a way of us cataloging where electrons are. Electron configuration was one of the first things that we teach students about structure in general chemistry. Orbital notation diagrams add another level of detail to an electron configuration. What they do is they take these different orbitals right here, and we specifically identify each of those orbitals, and we assign electrons to the orbital. So it adds, again, another layer of complexity. And we need that layer of complexity to understand what hybridization involves. Electrons are typically shown as a half-headed arrow. In the ground state, carbon is going to have 2 electrons in the 2s subshell, and then it's got 2 electrons in the 2p subshell, but we only fill 1 orbital at a time until they're all half filled, then we go back through and double up. So this is what the orbital notation diagram for carbon looks like. Once we hybridize our orbitals, what we do is we take all 4 of these orbitals and we blend them up. sp3 hybridization means that you grab the s and all 3 of the p's. sp2 hybridization, which we'll see later, is where you take an s and only 2 of the p's, and sp is where you take the s and 1 of the p's. For this carbon, because it has 4 electron groups, it's sp3 hybridized. I'm going to grab the s and all 3 of the p's. I'm going to blend them up and spit out 4 brand new orbitals. In order for the carbon to make 4 bonds, it's going to half fill each of those 4 brand new orbitals, and this is what carbon looks like. This is the model we have for carbon after we've hybridized it. Now we want to try to draw a 3-dimensional representation of what that would look like. So to try to understand that, let's first start off with what the original shapes of these orbitals look like. This is the shape, the approximate shape of an s orbital, and a p orbital is a dumbbell shape. The p orbital will orient itself in the x-axis, which is horizontal, in the z-axis, which is vertical, and the y-axis is a three-dimensional axis that goes kind of into and out of the plane of the screen or the laptop or whatever surface you're looking at right now. And I don't have a good way to draw that here on a two-dimensional surface, so I'm going to kind of tilt it, hopefully so that you remember that that black portion is pointing into the screen that you're looking at and the white portion is pointing out at you. Taken collectively, the three different p orbitals actually overlap here at the nucleus in the center. And even though each orbital is dumbbell shaped, their collective, kind of all three of them together collectively make up essentially a spherical shape. But we don't want to do that. All right, once we've taken these up and hybridized them, not only did we normalize the energy, so all four of them are the same energy, they're also all four going to have the same shape. And that shape is 1/4 of the shape is a sphere, and 3/4 of the shape is this dumbbell. And what we end up drawing is something that looks like this. And we have 4 of these. These sp3 orbitals are all, you can kind of see that, oh, the one side is kind of spherical and the other side has a remembrance of back when it used to be a dumbbell. And normally when we show sp3 orbitals, this little backside part right here just kind of gets in the way of our drawings. And so instead of explicitly drawing out the sp3 orbital, we have a habit of just drawing the fat portion of it because that's the part that actually does the bonding. So this is technically the shape of an sp3 orbital, but this is usefully the shape of the sp3 orbital. These 4 orbitals contain electrons, and so they're going to repel each other. I'm going to make them a little bigger here so we can kind of appreciate. And so this is where the idea of a tetrahedral molecule comes from. These 4 orbitals they'll all kind of sit on the nucleus, and they'll try to get as far away from each other as possible. Now, as far as being a good artist and trying to show this in 3 dimensions, clearly I'm not doing it very well. And I don't usually expect students to be able to draw these 3-dimensional diagrams with useful 3-dimensional perspective. And instead, what I ask them to do is just label the heck out of everything. So instead of you trying to draw this so that you can see the sp3 shape, I'm just going to ask you just to write a label directly inside of there. So we'll just go ahead and put sp3 right inside of there. This is the carbon. The carbon has 4 sp3 hybridized lobes. Spatially, you're welcome to kind of show those however you want, as long as you label them correctly. And so then I'm actually going to put the letter C right here in the middle so that I kind of represent the nucleus of the carbon. And it's going to not like that I'm doing that because it's going to tell me to put 4 hydrogens around that. All right, let's tweak this just a tad. All right. So this is what the carbon looks like. These are the lobes that are coming off of the carbons, and each of these lobes has an electron in it. And these are the electrons the carbon is offering up into a bond. In methane, the hydrogen is going to make a bond. A hydrogen is in the first row of the periodic table, and hydrogen only has an s orbital. It can't hybridize because there's nothing to hybridize. There's no p orbital to hybridize with for hydrogen. And so this is kind of what hydrogen does right here. And so we can just say that this is a hydrogen, and the hydrogen has an electron. I like to show the electron having the opposite spin, so I'll usually draw them like this, and then I'll make a big deal about that and then completely forget. So it's not a big deal to me that you do that or don't do that. I'll try to do it when I remember. So here are the 4 hydrogens that we have that surround the carbon. I'm just going to copy and paste that over and over again. Here's the second hydrogen, third hydrogen, and the 4th hydrogen. And this right here is try that again. This is my attempt to show a 3-dimensional model of what methane looks like. This is kind of a cleaned up version of this one. I think originally I had drawn it out like this, illustrating that I really don't care about the exact shape of the molecule so long as you put the labels in correctly. So in a correct 3-dimensional representation, we have all of the valence orbitals are participating, all the valence electrons are participating, and we've labeled the heck out of everything. So let's walk through some more examples of these and see if we can come up with diagrams for each one of these 4 compounds right here. The first one we'll look at is carbon dioxide. We've drawn Lewis structures for carbon dioxides in the past, and you always have to start with the Lewis structure. The reason you have to start with the Lewis structure is so that you know your hybridizations. So Lewis structure for carbon dioxide has carbon with 2 double bonds on each side. Oxygen has these 2 lone pairs. And let's go ahead and label the hybridizations. This carbon right here has 2 electron groups. Therefore, the carbon is sp hybridized. If you're going to sp hybridize something, that means that we're taking the s orbital and the p orbital, and we're spitting that out as 2 brand new hybridized orbitals. Energetically, they're kind of in the middle. So I kind of shoot for in between the s, which is lower, and the p, which is higher, and come up with these orbitals here in the middle. What I didn't hybridize and what remains unchanged, so these are my sp orbitals. I didn't actually do anything to the 2py or the 2pz. They remained unchanged. And so they stay. They're not hybridized, they're left over, nothing happens to them. And when the carbon, now in the hybridized state, prepares to make bonds, it's going to make 4 bonds. So I need 4 half-filled orbitals. And this is what the carbon is doing in preparation for making carbon dioxide. Spatially, in order to draw that, sp orbitals are those hybridized orbitals. The correct diagram for the hybridized orbitals, it looks something like this. But if you remember the little backside part, we don't care about, and so instead we just tend to draw our sp orbitals like this. We just show the front side lobe. And I've changed the color on you, that doesn't matter. Like what you choose to shade or doesn't shade, it's not important. The key is that when you show these hybridized orbitals, you show them as kind of this teardrop shape. Now, when you have 2 electron groups and your sp hybridized, that means that those orbitals are going to be linear. That allows them to be as far away from each other as possible. And so I'm going to go ahead and turn them. We'll put the carbon in the middle and go ahead and magnify things just a little bit so we can kind of see what's going on. We got these 2 sp hybridized lobes, so I want to make sure that I label everything. And we have a carbon in the middle. This is the nucleus of the carbon. Each of those sp hybridized lobes has a single electron in it. And we also have the other 2 lobes, the 2py and the 2pz. They did not get hybridized, so they are unchanged, and they're still centered around the nucleus of the carbon. Drawing those is a bit problematic just because of the way ChemDraw does it, so I'm actually going to use different colors. So this right here, the 2pz, if you remember, is the one I assigned the vertical axis to. So I'm going to go ahead, let's keep scrolling down. ChemDraw is kind of clunky when you zoom in. So by making this 200 times zoom up here, I slow everything down. So this right here is my 2pz orbital. The orbital exists in 2 places simultaneously. So this is half of the orbital up above, and this is half of the orbital down below. That's different than the sp orbitals, which this is all the entirety of the sp orbital, and this is the entirety of a second different sp orbital. But 2p orbitals exist on both sides. So half is here and half is here, and it still just has 1 electron. And sometimes that electron is up here on top, and sometimes it's on bottom, and I'm not going to show it in both places, so I'll just leave it in over here in the one place. The 2py orbital is a little harder to draw because it's the one that goes into and out of the plane of the paper or the screen or whatever object you're looking at. So I'll try to make it about the same size. Send it back to kind of give it some spatial perspective here. And then this one we bring to front and have it come out the front. So this right here is my 2py orbital. And there is also an electron in the 2py orbital because that's what I showed up here. Evidently it's a taller electron, so I'm not sure why. Okay, that's just a joke. They should all be the same size. I screwed up. Move on with my life. All right, this is the hybridization of the carbon. Now we need to show the oxygens. The oxygens each have a double bond, which count as 1 electron group, and lone pairs, which also count as individual electron groups. That gives me 3 total electron groups. Therefore, the hybridization, when you have 3 electron groups, is you grab an S, that's 1, a P, that's your second electron group, and another P, that's your third electron group. So when I hybridize this for the sake of the oxygen, this is oxygen. So I need to grab the S and 2 of the P's, and we end up making 3 lines. 1, 2, 3, and we have a leftover 2pz orbital, and that's what did not get hybridized. These are now called sp2 orbitals, and this thing up here is that unhybridized 2pz orbital, and this is for oxygen. And there's one other difference with oxygen, and that's that oxygen actually has 6 valence electrons. So the orbital notation diagram for oxygen should show the additional 2 valence electrons. When oxygen now has to take these 6 electrons and place them inside of this diagram, it follows Hund's rules, 1, 2, 3, and then I have 3 electrons left to place because there were originally 6 electrons. Oxygen needs to have 1, so let me say it this way. Hybridized orbitals always contain lone pairs, or in other words, lone pairs always find their way into hybridized orbitals. So I'm going to go ahead and put the lone pairs that I see in my Lewis structure. There's 2 lone pairs on this oxygen. I'm going to go ahead and put them in the sp2 orbitals, and now we can see that the other 2 electrons allow the oxygen to make its 2 bonds. In order to make a bond, an atom has to have at least 1 half-filled orbital. To make 2 bonds, you have to have 2 half-filled orbitals. The oxygen is sp3 hybridized. Let's go ahead and diagram what an sp3 hybridized oxygen looks like. If you're sp3 hybridized, that means you have 3 of these hybridized orbitals. So 1, 2, 3. These orbitals are going to get as far away from each other as possible. And to do that, they're going to actually make a trigonal planar arrangement. And so trigonal planar kind of looks like this. Okay? So just 3 points of a triangle. And then we have the other point of the triangle. It's right here. Okay, and the oxygen here is in the center. This is what sp2 hybridized look like. But I'm going to rotate this here for just a second. Having the oxygen be in the plane of the screen presents some problems. So what I need to do is kind of knock this thing over. So imagine taking your finger and pushing on this part right here so that the whole thing just kind of falls over. And what that ends up looking like is this. If I just take this thing and just kind of push it over, then this orbital, then it kind of knocks it flat. And these 2 orbitals right here end up being connected to the oxygen right here. Okay? Where one of them is kind of splayed towards me and one of them is splayed away from me. We show that kind of like this. We try to show some type of 3-dimensional perspective that I just took this little white patch of this orbital and poked it with my finger, knocked the thing flat, and this is the resulting diagram that we have. And the reason that we're going to do it like this is it makes it easier for us to see how all these things connect. These orbitals right here are the sp2 orbitals, so I'll put a label in here, sp2. This is my other sp2, and then this one here is also an sp2. I'll go ahead and take the oxygen right here. I'm going to go and do the oxygen over here on the left-hand side just because it's set up nicely for it. The oxygen takes its lone pairs and it puts them in these hybridized orbitals. So I'm going to go ahead and put a lone pair here. This is where the oxygen takes its lone pair. And then I'm going to leave an unpaired electron right here. Actually, I'm going to point it the opposite direction just so that it's easier to see how it matches up. This oxygen now makes a bond between this the hybridized sp2 orbital of the oxygen and the hybridized sp orbital of the carbon. I just clicked these pieces together, and this particular bond that involves the direct head-on-head overlap is referred to as a sigma bond, which we can actually just represent with the Greek letter sigma. So I'll go to symbol font. That's what a sigma looks like. So this is called a sigma bond right here. Okay. Now, I'm going to move this down a little bit. The thing, though, is that the carbon has this, the oxygen does still have this unhybridized 2pz orbital. And it's going to match up in the same plane as the 2pz orbital of the carbon. This oxygen has a 2pz orbital right here. It's always been there. I didn't actually use it for hybridization, and this is what's referred to as a pi bond. It is the side-on-side overlap of two orbitals, and it's a weaker bond because spatially this is a much weaker interaction. I'm drawing this pi bond occurring in two separate places, not because there are two pi bonds. There's still just one pi bond, but it is occurring both above and below. So you can think about half of the pi bond is occurring up here, and then half of the pi bond is occurring down below. It gets pretty tedious to write that in as half and half, so I just show that this is a pi bond, and I remember that even though I'm showing two dashed lines, it is a single pi bond. Okay, now we've got half of our carbon dioxide built. The other one is I got to build in this oxygen. And the nice part is every sp2 hybridized atom looks the same. So that means that the other oxygen is going to look just like this. There's a bunch of garbage here I don't want. I don't want that sigma bond there. I don't want this right here. Clean it up just a tad. It looks just the same. Shoot. I'm working with limited space. Oh, hey, I think I got everything. But I'm going to flip it. So we're going to flip this thing horizontally. There we go. And now this oxygen is connected over to this side. So this is the sigma bond on the left-hand side. Sorry, the sigma bond on the left-hand side. We have a sigma bond on the right-hand side. The problem is that I've got a problem. The other oxygen can't use its 2pz orbital to make a bond with the carbon. The carbon has already used this orbital to make a bond here. And so what this oxygen needs to do is make a bond with the 2py orbital. That should be, oh, we want to bring this to the front. We already did. All right, so in order to make this bond with the 2py orbital of the carbon, we actually need the oxygen to just rotate. And so the orientation A, or X, Y, and Z is kind of arbitrary. And so if the Z axis is already taken, then this oxygen will just simply shift that unhybridized p orbital over into the available axis. So it just kind of turns basically and uses now its 2pz orbital, 2py orbital to make the bond with the carbon. Go ahead and drop that electron in there. And we don't actually have to show both dashed lines because these start to get a little messy. So as long as we label everything correctly and call this my pi bond, now I have the correct three-dimensional diagram showing what carbon dioxide looks like. It has an sp hybridized carbon that is making a sigma bond through its hybridized orbital with the sp2 hybridized orbital of the oxygen, and a pi bond between the unhybridized 2py orbitals on one side and the unhybridized 2pz orbitals on the other side. Okay, so let's think about the four different types of atoms that we're going to encounter on a regular basis. Some atom A can be sp2 hybridized, which means it has three hybridized sp2 lobes and an unhybridized 2pz orbital. A different atom A could be sp hybridized, which means it has two hybridized sp orbitals and two unhybridized p orbitals, the 2pz and the 2py. Or you could have another type of atom, still called A, that is sp3 hybridized with these four lobes coming off of it. And the only other atom that we'll run into on a regular basis is hydrogen, which hybridizes in a 1s fashion, which doesn't hybridize, it just stays 1s because it can't hybridize at all. So now let's look at the other example that we have, and that's formic acid. It is a carboxylic acid. This is from the PowerPoint, and it has a carbon in the center with a hydrogen on this side, on the left side, and an OH group over here on the right side. And we should be able to just use these different types of atoms that I have shown as templates. So this is what carbon dioxide looks like, formic acid looks like. And all we need to know is the hybridizations. It's got a hydrogen over here on the left-hand side. Let me bring these up a little bit. I'm going to show you how I'm just going to slap together these four different styles of atoms to make formic acid. We have a hydrogen that's over here on the lower left. I'll just dump it down here. This carbon right here is sp2 hybridized because it has 3 electron groups. So this is an sp2 hybridized carbon. Now I might have to rotate these things a bit to get everything to work. The hydrogen right here is going to stick to one of the sp2 orbitals. Let's see, how do I want to do that? Yeah, this is going to be kind of a messy one. Okay, and let's move this up and out of the way. Oh, dang it. Okay. Then, and now this is a carbon atom, so I'll go ahead and draw the label for carbon right here. We have an oxygen that it's connected to. That oxygen is also sp2 hybridized because it has 3 electron groups. So I'm going to grab this as an oxygen and bring it down over here. We're going to flip it horizontally so that the 2 hybridized orbitals stick into each other to make a sigma bond. So there's my oxygen. That shows both the sigma bond between the carbon and the oxygen, and the pi bond is up here. We have another oxygen that's going to be stuck to this sp2 lobe, and that oxygen is sp3 hybridized. So sp3 hybridized atoms always have the 4 different sp3 lobes coming off of them, and they're going to form a sigma bond by sticking one of their sp3 lobes into the sp2 lobe of the carbon. So this is now an oxygen atom. And then we have a hydrogen that's connected to any one of those sp3 lobes of the oxygen. And I'll stick it over here. Okay, so I've kind of got everything diagrammed out just by copying and pasting these template structures. The carbon and the oxygen have a pi bond that are connecting them together, and the rest of these bonds are all sigmas. So I'll go ahead and make up some of my sigma labels. It's a good habit to go ahead and drop labels on each of these types of bonds just to prove to me that you know what these mean. So that's a sigma bond right there. This is a sigma bond. Whenever 2 orbitals run directly into each other, that's a sigma bond right there. And then the only other type of bond that we're going to encounter in this course is going to be the pi bond, which was a symbol. All right, finally, let's drop in our valence electrons. Carbon has 4 valence electrons, 1, 2, 3, 4. This oxygen over here is going to have 6 valence electrons. This oxygen right here is this oxygen right here, and its lone pairs will end up in these hybridized orbitals. So we're going to put lone pairs here and here. It's going to have a single electron in the 2pz orbital that allows it to make a pi bond, and a single electron in the sp2 orbital that allows it to make a sigma bond. This oxygen over here is going to be a little harder to show because I've got to color code this white and then not lose it. So there's 1, 2, 3, 4, and then the oxygen that's connected to the hydrogen, this oxygen right here has 2 lone pairs. So there's one of the lone pairs, and there's my other lone pair. So that is the diagram for formic acid. And the point of this question was to show you that once you have down your 3 types of hybridizations and an unhybridized hydrogen, you can pretty much use that same diagram as long as you rotate it or twist it however you need to draw out all of the 3-dimensional diagrams that you need. If you could make a stamp set that would just stamp this diagram, then you could just use a stamp, punch it down on your paper, and then fill in the orbitals with the appropriate labels. Molecule in that the nitrogen is in the center. You got nitrogen on one side and an oxygen on the other. This is an inorganic molecule, so we want to build this according to the rules of inorganic chemistry. We count up the total number of valence electrons. Each nitrogen has 5, oxygen has 6, that's 16 total. I have spent 2 here and 2 here. I'm going to put, this is electrons 5 and 6, 8, 10, 12, 13, whoops, I lost count. 2, 4, 6, 8, 10, 12, there we go, 16. 2, 4, 6, 8, 10, 12, 14, 16. Yep, there's all my electrons. Okay, now in terms of fulfilling the octet, this N2O is a bit of a trick just because it's hard to come up with it. But essentially what you're going to have to do is drop both of these down. Oh, that was the erase button. You have to drop both of these lone pairs down here to make a triple bond. And when you do that, when I make this triple bond right here out of those lone pairs, it gives everybody an octet, but it creates some problems in terms of the honk X rules. And that's kind of the weirdness of this particular compound. There's no way to draw this molecule without having a positive formal charge on the nitrogen and negative formal charge on this oxygen is the best resonance structure option. So here's my Lewis structure. Always start with the Lewis structure. Once you have the Lewis structure, we assign the hybridizations. So this atom in the center has 2 electron groups and is sp hybridized. This nitrogen here also has 2 electron groups and is sp. And then this oxygen on the far left is sp3 hybridized. So if we look at an sp hybridized nitrogen, we're going to take our sp hybridized stamp and drop it down right here. And the other nitrogen is also sp hybridized. So we're just going to touch those 2 sp orbitals together to go ahead and make our sigma bond. We'll have one pi bond occurring between the 2 pz orbitals and the other pi bond occurring between the 2 py orbitals. The oxygen out here on the end is sp3 hybridized, so we grab the sp3 hybridized version, and I'm going to rotate it just a bit so that I can connect this to the other sp. We'll go ahead and draw in our atom labels. So this is an oxygen, this is a nitrogen, and this right here is also a nitrogen. I'm going to go ahead and put some lone pairs of electrons. So oxygen should have 3 lone pairs of electrons, and those have to be colored white. I made a poor choice there when I built this diagram. Let's start over here with the nitrogen. Lone pairs always end up in hybridized orbitals. So this nitrogen's lone pair will end up over here in that hybridized orbital. And then let's go ahead and color code these white so I can put them against a black background. So this oxygen is going to have 3 lone pairs. 1, 2, 3. And we need 1 electron to put right here. Now here's the trick. If I can even see that. Yeah, there it is. Okay. When an atom carries a formal charge in its Lewis structure, that actually reflects the number of valence electrons you give it in these 3-dimensional orbital diagrams. So if something has a -1 formal charge, that means it's going to end up with 1 additional valence electron. Oxygen's supposed to have 6, that's why I've given it 7. If something has a positive formal charge, then it should end up with 1 fewer valence electrons. Nitrogen normally has 5, I'm only going to give it 4. So I'm going to put 1 here. I don't know why that flipped on me. 1 here in the 2pz, 1 in the 2py, and 1 in the sp. This nitrogen over here is a normal nitrogen with 5 total electrons. I've already given 2 as a lone pair. There's 3, 4, and 5. All my valence electrons are placed. Let's go ahead and make my sigma and pi labels. We'll turn that into symbol font. This one here is also symbol font. And I need my connector for pi bonds. Pi bonds occur here and between these 2 pz orbitals and the 2 py orbitals. This is a sigma bond. This is also a sigma bond right here, and then I should have 2 pi bonds. The total number of sigma and pi labels that you drop in your structure should add up to be the same number of lines that you drew in your Lewis structure. What I mean by that is in my Lewis structure right here, there is 1, 2, 3, 4 lines. So I should see 1, 2, 3, 4 sigma or pi labels. Our final example is sulfur dioxide. Sulfur dioxide is actually a Lewis structure that we've used a couple of times in this class, well, at least once. Now makes it a couple. So here's the Lewis structure of sulfur dioxide. Notice how the sulfur ends up going above and beyond the octet rule, and that's going to matter to us in just a second. As far as hybridization goes, all 3 of the atoms in my structure have 3 electron groups. So I'm going to use just a bunch of sp2 labels. So we'll grab this sp2 and drop it down here. That will be the one oxygen. Let's put the other oxygen over here. And I'm going to flip it horizontally. So this is the oxygen on the right-hand side. It's sp2 hybridized. So I went ahead. I've got it ready to go with my template of what every sp2 atom looks like. The oxygen on the left-hand side is also sp2 hybridized. And the sulfur is not quite the same template. So let's go ahead and copy this down. For one thing, it's no longer a second row element. So this is actually, for sulfur, it's going to end up being 3pz. And as you go down the periodic table, the atoms get larger, and so I can go ahead and just kind of illustrate that by trying to expand it. I'm going to grab the corner. There. Now it looks a bit more like sulfur. So sulfur is a big one, and it bonds to the oxygen. So we're going to stick it over here on this side to this oxygen, and that is my sigma bond that I've already got lined up between the sulfur and the oxygen on the right-hand side. Remember that a sigma bond is the head-on-head overlap of orbitals. I'll drop some electrons in there. There's no formal charges on any of these atoms, so every atom should have 6 valence electrons. We'll put one here for the sulfur, one for the oxygen. The oxygen has lone pairs. Lone pairs always go into hybridized orbitals, so I have a lone pair here and a lone pair right there. The sulfur also has a lone pair. Lone pairs always end up in hybridized orbitals, so I'm going to dump them over there. The final electron for the oxygen, so I've got 1, 2, 3, 4, 5 total electrons. I'll put my 6th right there in the 2pz, and I'll put a corresponding electron over here in the 3pz. The sulfur has 1, 2, 3, 4 total electrons. I'm going to put a 5th electron right there. And you might already be ready to ask, where am I going to put that 6th electron? Give me a minute. It's a little weird. So here we can make a pi bond between these two atoms, between these two orbitals. It's actually the 3pz orbital of the sulfur overlapping with the 2pz orbital of the oxygen. The fact that these orbitals are not the same size, one of them's longer than the other, does create a significant problem. And there is substantial debate as to whether or not pi bonds truly form between elements on different rows of the periodic table, or if the differential sizes actually prevent that from occurring. That's not a debate that we're going to wade into. The issue now is, what do we do with this other oxygen? Well, it also has 6 pi electrons, so let's go ahead and drop, I can drop 2 in right here and 2 right there. And then it's got 6 total valence electrons, 1 valence electron is going to go ahead and make the orbital overlap, and then 1 here in the 2pz. In order to get those to kind of stick, it's this orbital right here needs to interact with this bottom sp2. And so if I want, I can turn it just a tad to kind of show that that's generally kind of a linear extension across those orbitals. And that's what gives me my sigma bond. The problem is the pi bond. Sulfur needs to make another pi bond with this oxygen over here on the left-hand side. And sulfur doesn't have any more s or p orbitals to make that pi bond. When you sp2 hybridize something, then you have 1 p orbital left over, and I already used that to make the 2pz, 3pz pi bond on the right-hand side. So on the left-hand side, sulfur is going to have to use a different orbital. And the only orbitals that I have left that are available are d orbitals. Sulfur is a 3rd row element. It's gone above and beyond the octet, so it's definitely going to use a d orbital. The shapes of d orbitals are not that important. This model, actually, this is a diagram that shows a potential shape. D orbitals come in weird shapes. This is an actual potential shape for a d orbital. It tends to go through the axis of the compound, which would have a hard time. I mean, it would kind of line up with the 2p that's on the oxygen on the left-hand side, but I don't like that one for reasons that are not part of this class. So let's actually use this. This is a diagram of a d orbital. D orbitals actually have 4 separate lobes coming off of them. And me spending the time picking a correct d orbital, the one I really want to use, is actually a problem because I don't care what shape you use for d orbitals. Any shape that you choose to use for your d orbital is fine. And d orbitals are quite large, like they're pretty big. and getting that all to fit in here starts to become problematic. So d orbitals are big orbitals. They actually have up to 4 lobes coming off of them like this, and they'll overlap with the 2pz here, and then the other part has to overlap with one of these other lobes. I forget exactly how that works. Because normally what I do with students is I'm just like, you know what, it's too messy to draw it like that, so you can draw any shape you want for a d orbital. I don't care, as long as you label it correctly. I have hopefully already established in class, and if not now in the video, that I expect very low artistic ability. And so as long as you can label stuff, it really doesn't matter how you draw it. So for the sake of simplicity, I'm going to, I'm just going to label this as a 3D orbital. The d orbitals come in different flavors, like you have 2pz, 3pz, z, x, and y for the p orbitals. You also have similar arrangements for the d orbitals, but I don't care. I just want you to tell me that you understand that the d orbital is what's going to have to make that pi bond right there, and that's how sulfur makes its second pi bond. Pi bonds are defined as a non-linear overlap. And so anytime you have 2 orbitals that are coming together that's not in a head-on-head collision, then we're going to call that a pi bond. There's actually something else called a gamma bond, I believe, which we could maybe call this, or delta bond. I can't remember, and I don't care. I just want you to show me that the d orbital is involved in making some type of interaction, and label the d orbital, and then draw it however you like. If I'm drawing them on the chalkboard, I usually draw a dragon's head, just for the sake of doing something different. I don't care what they look like. I just want you to label it correctly. Just to wrap this section up, these are the textbook sections that correspond to today's class. The actual three-dimensional drawings that I'm doing are something that the textbook shows you and then doesn't spend a lot of time talking about. And so there's not a lot of great practice problems that I have for you to draw these three-dimensional structures. But I think if you can review these 4 examples I've got here for you, and if you want to look over the methane and formaldehyde as well, that should illustrate all the different variation that we see with these three-dimensional diagrams. The purpose of today was to talk about the nomenclature of simple alkanes, identify hybridization of atoms in Lewis structures, and then draw three-dimensional structures of the simple molecules that emphasize the hybridization. Hybridization.